Hello everyone, good morning and welcome to our Digital We Days, to the first session. And yeah, I'm very happy to welcome all of you, and we are very happy to that you participate in our webinar this morning. My name is Markus Eberle and I will moderate this session today. The topic is about LTSpice for the validation of power converters. Our speaker today is Sylvain, who is working as a field application engineer at Würth Elektronik. Before we start the webinar, I would like to point out one thing. You will be muted during this webinar today. This means that you cannot ask us questions via the microphone. Nevertheless, you have the opportunity to ask us your questions with the Q&A function of the webinar, of the WebEx. You will find that on the lower right-hand side. The webinar will be about 30 minutes long. After that, we have scheduled 10 minutes for the Q&A, and we will go then into your questions. If we can't answer all your questions within this live webinar, we will answer them later on via email. And you also have the opportunity to ask us your questions via email at digital-we-days@we-online.com. And of course, we will try to answer all your questions promptly. You will also receive the link to the presentation you will see as also with the recording of this webinar later on from us via email. And you also have the opportunity to find all that information on our homepage. You will find there also the possibility to register yourself to our other sessions of our Digital We Days week. So I think that's said enough for the start. I'm happy to give over to Sylvain, and I wish you a good webinar. Thank you.
Thanks a lot, Markus, for the introduction. So let's begin. So let's make the computer work for us. It's quite a good trend in these days, but we will see today how we can use our computer to cut down the validation time of a power converter. Because letting the computer work for you is a science. So we will see the use of the PWL test vectors to test our converters, mainly the load profile today. The presentation is only 30 minutes. It's a very, very short timing for me. So you see some of the subjects are crossed because we will not be able to handle them today. Then the next thing for me, which is very important for the validation, is how to be able to iterate the simulation. And while we iterate through the simulation, we need to change a few parameters or else it will make no sense. So we're going to see how we can change a set of parameters and how we can also use the randomization to pick any value between two boundaries. Then we're going to dive deep into the measure statement. First, a basic usage, then advanced usage to, for example, compute the power factor. And then we're going to see how we can summarize hours of simulation, days of simulation into one single plot. Then the last thing for today would be the exotic plot coordinates. The safe operating area of a MOSFET is one of them, but it's very useful if you want to be able to validate from the simulation if your MOSFET is going to survive what you're going to ask him. And then at the very end, we're going to see the thermal transient or SOA term validation. So this SOA term validation is a brand new feature from LTSpice 17, and it's really helpful for the designers to validate the thermal behavior. So now back to section 1, the usage of PWL test vectors. So PWL test vectors. The PWL means piecewise linear, and these vectors are used to generate specific waveforms. So here we're going to cover the generation, acquisition, and use of PWL test vector. So here, for example, I've decided to replace the output resistor of my simulation with a PWL source, which is a load. So what we can see here is that our PWL vector is enclosed into a file. In the file, we have on each line a pair of values. The first one is the time, the second one is the value that we want to apply. It can be volts, it can be amps, it can be a lot of different values inside this PWL test vector. So the good thing with the PWL test vector is that it can enable you within one single simulation to validate multiple scenarios such as overload, load transient, and startup. We're going to see how we can use that a bit later. So here I've created here by hand my test vector to be able to generate the stress on my converter. So obviously you don't have to generate everything by hand. We were going to see this a bit later. So here is the advanced settings of my independent current source, which is the output of my converter. So I clicked in a PWL file as a source, and I input my load profile text file. So by adding this load profile text file in my simulation, I'm now able to generate a variable load at the output. So here, our PWL file load profile.txt and our simulation cover roughly the same time range. So let's run the simulation. And you can see here the magic that happens when you use these test vectors to validate your schematic, your power supply schematic. With only one run of simulation here, we are able to validate a lot of scenarios. And that's very important to be able to validate out of one single run several scenarios because it will cut down validation time from the same factor. So here, the first thing that we do is get to a plateau here of 1 amp. This 1 amp plateau enables the converter to start up and to stabilize at its nominal voltage. Then we're gonna abuse of our converter while overloading the output. As we overload the output, we can see here that the current increases while we empty the bulk capacitance at the output. And once the output capacitance is down, then we see we are back at 0 volt at the output for a certain time. Then something which is very important for the designers is the way that you recover from a short circuit condition in your power supply. So is my system dead or is it going to start up again? So as we can see here, we are just around the current limit at the output and the voltage is quite low. And as we release the overload, which is here the section 2, we can see that we are increasing back the output voltage. And as we release the load here down to 0 amp, we see that the output voltage is now back into almost normal situation. It's a bit more than what we are expecting at the output, but still it's okay. Now we enter another phase, which is the light load and no load, and to see what happens with this light load and no load condition. So what we have here in section 4 is having a slight ramp of current and then getting back to 0. And we see that this stimulus, this output current ramp creates a drop into the output voltage. And then we get to the most typical testing that we often see in data sheets in application notes. It's called the load transient, section 5. So the load transient on section 5 is just stressing the output of a converter, testing both its ability to regulate to answer fast and not to have overshoots and oscillations in its response. So what we can see here is that going from 0 amps to 3 amps just creates a little dent in our output voltage, another shot, and then stabilizes. So I would consider that this kind of answer of the DC-DC voltage is okay for me. So you see the power of just one piece of piecewise linear test vector for the validation. We have just started a few minutes ago, and you are now able to validate within one run of simulation a lot of parameters of your DC-DC converter. So now the things that are interesting to know is you can also, if you want to test a bit more with repetitive patterns or to reach an asymptotic behavior, you can use the repeat forever and n repeat directive. This directive will enable you to repeat the load profile that you have in your TXT file, so you can reach a longer simulation. The good thing with PWL principle is that it applies to many components. They can be current sources, so be careful, because when you use the I3 current source, if you request too much energy, then you're gonna have the voltage at the bound bar at the here I3 that is going to be negative. So then you can apply this PWL also to the voltage sources, and here, for example, and here, as we use in our example, you can apply this to a load, so you don't have the same glitches that you would have on the I3 kind of source. Obviously, you don't have to generate everything by hand. When I need to test a lot of conditions, when I need to test a lot of transitions, I use a generation with a program. So this is the example on your fraction of a program of a C program that is generating me the files that will be used. So here I'm just printing into a file my value and time pairs into the file. Here I can have also the possibility to change the rise time and the fall time, and the low output voltage and the high input voltage. So this is an example of generation for test for signal integrity, but it also works to generate a random load at the output of a DC-DC converter. So now let's get into the iteration and functional validation. So here we can have a look at one of the most important directives in LTSpice, and we will see how powerful it is, especially if we want to later have iterations of our simulation. And we're gonna try to sweep these parameters. So the first thing before sweeping them is declaring them and knowing how to use them. So the good thing with the parameter is that you can use it both in a component, an expression, and you can also decide to use it in multiple components. So this gives you the ability to change with one single parameter the behavior of an array, the behavior of parasitic of three identical windings in a motor, for example. The usage in an expression is, for me, very, very interesting. You're going to see in the next slide, because you can use the basic mathematic equations to modify the way that you are using this parameter. So here, for example, I'm using the square root of the capacitance value. So since LTSpice 17, you might not know, but there is a statement editor, and it's very convenient when you want to add on a single line multiple parameters. So to have access to this statement editor, you just paste your .param directive on the schematic, and then you click on it again. And when you click on it again, then you will see you will have this statement editor, enabling you to just input as much variables as you want. So here is an example of what I'm doing with the parameters. So now I'm generating with these parameters the signals that will be used for the driving of the MOSFET. So here, for example, as you can see, I'm using here the TDiv, T-rise, and T-fall, and here again the TDiv. And here the time that the location of the on time and the period are changed by using the relationship between these. So here, each of the MOSFET is driven by a source, and each of the source has its own turn on time. So here, for example, you can see that it's the 3-time division, and here 6-time division, here 0-time division, here 2-time division, 5-time division. It might be a bit complicated, but it's the easiest way to generate a test vector, to generate actually 6 test vector that are going to run a simulation which is very representative to what happens in a real BLDC motor drive. So here is the example of what happens at the end of a simulation. So you can see here that you can easily adjust with just changing the parameters, the slope, the dead time, and the frequency that you are using in your simulation. So for me, it's the real power that you have with a parameter is to be able to change only a very few things when it comes to values and drastically change what is happening in the simulation. So now another thing with the parameter is to be able to iterate the simulation and use this iteration to generate and to sweep over several use cases. So here is an example of a filter. So here is my filter, C1, U1, which is a ferrite, and C2. So what we can see here is that we are stepping over the parameter DCV. DCV is the DC voltage overlay, which has been added on top of our AC source. What I'm doing here is I'm testing the DCV overlay from 0 volt to 10 volt in step of 1 volt. By doing this, I'm able to stress my filter because my filter is not going to answer in the same way if I have DC bias on the C1 capacitor, if I have also DC bias on the ferrite. So this is a saturable ferrite model. So now what we can do is run the simulation and see what's the impact of the DCV on the frequency response of our filter. So here is the result. So we have 10 steps now, and these 10 steps are just on the same plot window. So what we can see here is that it's not easy to know which one is the 0, which one is the 10 volt simulation, but for sure it has a huge impact on the frequency response. To polarize our filter with 0 to 10 volt will just not yield the same result, because here mainly we have the DC bias of the capacitor, which is changing the frequency response. So to get a hint about in which direction is it moving, we can decide to display the step legends. So the step legend is accessible through the menu, view and step legend, and now it's much easier to read. So as we can see here, the higher is the voltage, the higher is the resonance frequency of our filter. And we can also see that the lower is the voltage used to polarize our filter, the more effective it will be if we consider it to be a low-pass filter. So we can see here is a logarithmic scale. So the difference between this yellow curve and this blue curve is actually huge, even if it does not look like this on the screen. So the other good thing to know about the plot setting and the steps is that you have a directive that enables you to extract directly from the naming of a trace to have one specific step. So here, for example, the arrow base 1, arrow base 9, arrow base 5 stands for the specific steps in the simulation. So you see that I can directly decide to extract one of the steps from my simulation, which is very useful if, for example, I have checked in my SPICE error log that we will see later that the step number 5 is just not behaving like expected. So now that we know how to iterate to sweep parameters, let's look at the way that we have to do more iterations and to sweep the parameters in statistically distributed ways. So this section is called adding some randomization to the simulation iterations. So you can see here that some are more random than others. So it's a very useful tool for statistical validation, mostly for tolerance components. It's ideally suited to run during coffee breaks, lunch breaks, and nights. And as you can see in France, the lunch break can be as long as nights. So LTSpice enables you also to plot against any variable. So here, for example, you see in this plot, I'm using the run here as an x-axis. So out of this very single image, you are having the result of 1,000 run of simulation and 3 different distribution, worst case, Monte Carlo, and Gaussian distribution. So the first thing is the worst case distribution. So it's not a built-in function in LTSpice, but the worst case distribution is the best way to perform gross validation of your design. So it's not covering a lot of things. You see, it's the purple line. As you can see here at the very end, it tests with the nominal value, it tests with plus the tolerance and minus the tolerance. So it means that the coverage of the worst case distribution is not very good, but it's very good for a rapid validation, or if your simulation needs days or hours to run. So here, for example, is the declaration of the worst case scenario. And here you have the nominal value, the tolerance which is applied, and the index. So the index is a very important thing because you can decide to plot, for example, 2 different indexes. So you will test the plus tolerance on the first index, minus tolerance on the second index, etc. So to use this function, there is one manipulation which is required, which is to copy these 2 lines, which is func worst case and func binary. So these 2 lines have to be copied on your design to be able to use the worst case distribution. So now the Monte Carlo distribution. So we're not talking about the blue lines that you can see on the enclosed between the purple lines. So here the blue lines are Monte Carlo distribution. For me, it's a very convenient way to validate a lot of designs, but it will not have more samples at the center of the distribution like the others. So what we can see here, it has a uniform distribution of sample within tolerance. So it's not validating anything outside the tolerance. But still, you will need a lot of simulations to get a good coverage. The good thing now is that this function is built in LTSpice, and you don't have to copy and paste anything to use it in your simulation. So to use it, you just have to declare Monte Carlo, the nominal value, and the tolerance which is applied. Here I decided to have this parameter to model my tolerance, but you can directly place this 0.1 here instead of TOIA, tolerance A. The last one is the Gaussian distribution. It's using the normal law or the bell-shaped distribution, depending on the country you're living in. For me, it's the most convenient way to validate a simulation because it will pick values outside the tolerance range, something which is likely to happen sometime. But it's a choice for you because some of the components are not supposed to be outside of the tolerance, even when you're browsing through the whole temperature range. So the good thing here again is that this function is built in LTSpice, so you don't have to modify anything except adding this kind of simulation, this kind of distribution here. 1 plus Gaussian with the tolerance that you will apply to the Gaussian, which is the standard deviation here 0.1. So now let's see how we can run this simulation and how we can use our Gaussian distribution, our statistically distributed variables. So here I've created a very simple schematic, which is composed out of a divider bridge with two resistors having a nominal value of 1 kilo ohm each and a tolerance of 50 ohms, which is 5%. But here I have added a capacitor, and this capacitor, like many ceramic capacitor of high capacitance, has a huge tolerance. So here is a 50% tolerance on the capacitance value. So here I'm using Monte Carlo simulations, so which means I'm going to pick values within the tolerance at each draw of the simulation. So here is the important thing, the step param run 151. So here it means that I will run the simulation about 50 times. And by running the simulation about 50 times, here is the kind of result that I get. So as you can see, here, for example, if we have to decide what is the minimal voltage to consider that it's a logical one, what is the decay time, we can apply a lot of strategies to use this kind of information. So you can see here the wide distribution that we have in the components. We can see what is likely to happen, what is not likely to happen, where is the average. So it's a very convenient way. I think you're going to do much more interesting thing in your validation of your design, but here's just an example of how easy it is to set up iteration in your simulation and to get some valuable data out of it. The next thing for me is just to extract a very concise answer about is my system working or how is it working. So the next thing is the measure statement. The measure statement is the ability for you to automate what you were probably doing with cursors. So here, for example, I'm looking for the peak MOSFET voltage here. This voltage is going to see some high voltage when it tries to block the energy. Then the secondary diode voltage, and then another validation I want to do is the power that I have in my MOSFET. So by using the measure statement, I'm able to have all this information directly into my SPICE error log. So when I run the simulation, what I can see now is that I'm having this kind of information. So the SPICE error log is accessible through the menu. And here I get my secondary diode voltage, which is 8.64 volts, my peak MOSFET voltage, 125 volts, and the power in my MOSFET, which is 0.54 watts. So is it okay? Is it not okay? Do I need a bigger heatsink? Do I need to shorten the transition time? Then already from this very simple thing, it enables me to pick the techniques that I'm going to use to cool my MOSFET down, to select my MOSFET in terms of breakdown voltage. For me, it's very convenient. But now let's combine this measure statement with a plot of the input voltage. So I've decided now to add the step parameter here of DC voltage at the input. So the DC voltage at the input now is going to sweep from 30 volts to 60 volts in steps of 2 volts. So this simulation is obviously going to take a few minutes, and you will see how fast it is to check out the result. So now our SPICE error log does not look the same. It's rather look like an array of results, which is not always very convenient, but still it's a very synthetic way to display the results without having to browse through the curves. And now the good thing is I can plot the stepped measure data. And by plotting the stepped measure data, I'm now able to get the trends of what is happening. So here, for example, I can see that the worst case scenario for my MOSFET is between 52 and 54 volts at the input. the secondary diode voltage is increasing linearly with the input voltage, and so does the peak MOSFET voltage. But we can see here it goes from 125 maybe to 158, 56, 58, while going from 30 to 60 volts at the input. So you see how powerful it is. It's like summing up a lot of simulation runs into one very screen with three different plots. So the most important thing for me is to be able to do a succession of calculation to get some valuable information. So here, for example, is the power factor calculation. So the power factor calculation is just nice to have information when you want to check if you're conforming 61-3-2, for example. So here, the trick is that I'm adding out of a single SPICE directive several lines. And as you can see here, by adding them into the same directive, I'm making sure that I will be able to use the results that I generated on the previous lines into my power factor parameter calculation. So here, for example, I'm calculating the power factor by using the parameter power, which comes from the third line, I average, which comes from the first line, and U average, which comes from the second line. So it's really enabling me to get my power factor here, which is 0.95. So here is the example of the power you can have with this kind of simulation. This comes also from the Spicer log. It's always at the very same place. And now you have validated your power factor, and you know that you can directly offer this to the next step of the design. Then for today, we're approaching the end of this presentation. So it's the exotic plot coordinates and the usage. So the safe operating area of a MOSFET. So obviously this one is the simple version. It's not the time-weighted version, which is present in the longer presentation, but it's also good to know that you can do this very simple and quick validation. So here is the safe operating area of a MOSFET graph. So on this axis, you have the drain to source voltage, and on this axis, you have the drain current. So there are regions where you should not go, and there are regions where you should not be able to go. In red is the area where you should not be able to go because it's restricted by the fact that you don't have zero resistance, so you should not be able to get in this area. So we'll not consider it too much. If you're getting through this area in the simulation, it means that it's probably a glitch because you're going from positive to negative drain voltages. Here is in purple is the overcurrent area. The overcurrent area here is the place where you are susceptible of having a destruction of your device because of overcurrent. Here in green, what you have is the overvoltage area, the breakdown voltage area, which is the region where you are susceptible of destroying your MOSFET because it's not meant to block such high voltages. And now we're going to see how we can stay within the limit and check if we are within the safe limits. So the safe limit is a fraction of the white region. And depending on the time you're spending in these regions, you can go further and further. But if you are planning to stay, for example, longer than 10 microseconds, do not get in this region of a combination of voltage and current in your MOSFET, or else you will destroy it. It's the same if you're not starting from original temperature of 25 degrees, do not get as far in these regions. So the good thing with LTSpice is that we can use the horizontal axis to plot versus almost any quantity. You've seen before that I can even plot against the number of run of my iterations. But here, what will be interesting for us is to plot in the same quantities and in the same axis properties that we have in the safe operating or area of MOSFET. So here is the example of browsing through the safe operating area. Here are the glitches I mentioned when going from positive to negative voltage, so you don't have to bother about these areas. And here you've already seen, if you've seen the previous presentation, that we can use the graphical elements in the plot setting window to draw some lines. So here I've decided to copy and paste the coordinates of my safe operating area and to put them directly into my display. Having them directly into my display enables me to check whether or not I'm approaching the maximum voltage or the maximum current. And in this simple simulation, we don't wait the time that we spend, but it's already enabling us to see that we're not overstressing the MOSFET and that we have to care about the region, the areas where we have both a lot of voltage and a lot of current, which is roughly here 15 amps and 120 volts. So the last thing for today is the SOA term functions. The SOA term functions are thermal simulation built in LTSpice. It's a new feature of LTSpice 17. It's a macro model that you had on top of your schematic, on top of your MOSFET. And this model enables you to have access to the junction temperature and to the solder temperature. It also enables you to add a virtual heatsink. And this virtual heatsink here has many properties, and it really helps you to define whether or not your system is likely to be properly cooled down. So here, for example, you can define the PCB size. You can define the contact area of your chip. So here is 8mm by 8mm, so which makes a 64 squared millimeter value. I can define the copper thickness, which will also increase the thermal impedance and the conductivity in big power planes. I can set the ambient temperature. Here is 85 degree, and here is LFM, is the amount of air which is flowing through this against this area cooling down. And I can eventually select the material which is FR4 of 1.5 millimeter thickness. So as soon as we have that, we will have voltages here at T junction and T solder. And these voltages will actually represent some temperatures. And by representing the temperatures, it really enables you to understand why your MOSFET the last time was dead. Because, for example, here what we can see is that the junction temperature is increasing very, very, very fast in terms of milliseconds, even fractions of milliseconds changes, while the solder temperature takes takes a relatively longer time to answer and to reach the same temperature. So you can see here, it's written voltages here, but they are actually Celsius degrees. And you can get into the simulation for that because it's really a very convenient way to handle the pulses and to see whether or not your MOSFET is going to survive what you're trying to do with it. So thanks for watching. I don't know exactly my timing. I hope you enjoyed this presentation, which is very a shortened version of the presentation and only a fraction of it. I think you already know the Anticipate EMC with LTSpice, where we started to use LTSpice for things it was not really meant for. And soon I am happy to announce that we will have a new article together with Analog, which is signal integrity with LTSpice. And if you're French, you already know this presentation, but we're trying to make it international, which is LTSpice for EMC filter design. And I hope I will be able to present you some more webinars covering the extensive use you can make out of LTSpice for the validation of any electronic system. Thanks.
Thank you very much from my side, Sylvain, for your interesting presentation. So time-wise, we have to hurry a little bit because of our digital V-Days. We have the next session incoming, but we have still some time left. So I would start into the question and answers. Sylvain, by the way, you can also stop sharing the screen. Then we see us more main on the screen. So then first question, Sylvain. Can we use the PWL files to generate normative searches test waves?
So the normative search test waves are generated out of hybrid converters. So they do feature more information. Charged all the voltage protection principles. If you don't mind, I will share my screen again. Sorry for that. We will not see each other.
Of course, you're welcome.
For a few seconds. Share screen, where is it? More options, sharing content, sharing the whole screen. So to generate the normative test setup, what you have to use is a search generator such as this one. So as you can see here, it defines two different waves, one on the shorted output here, and one on an open output. So there is a bit more components that you need to have to generate these surge voltages as they are in the 61000-4-5 combined wave generator. So it's possible, you have all the values here if you're interested, but it's not possible to use a PWL generator to do that.
Okay, so thank you very much for your answer. Then we will switch to the next question. Can you show or share the source code of the waveform generator?
Yeah, it's I can share it. Here is it's a quite short program. It's a C program that I'm using. I will share my screen after a few seconds. Just let me browse through the files. SD software and PWL generator, and here is PWL generator. So sharing my screen again. Share. So here is the example of the generation. So here I have, for example, a bit more complicated bitstream generator. Bitstream generator here is using logical levels, and it's also adding, because it's for signal integrity, things as bit stuffing, where to avoid having too much consecutive same polarity bits. And here, for example, I'm adding a lot of extra levels. So this one is a bit more complicated, but as you can see, it's always the same. You define a few parameters in the beginning of a program. We loop for every sample, compute the sample, and write the sample down in the file. So at the very end, we close the file and it's ready to use within LTSpice.
Okay, thank you very much. So then we are at the end of our webinar. Thank you very much for your attention. Also, Sylvain, thank you very much for your time today.
Thanks, Marcus.
And yeah, you are welcome. And I hope you will tune in our other sessions as well. And yeah, keep you updated. If you have any questions, or if there are any questions open, we will answer them later on via email. And yeah, So then have a good week. Bye.
Thanks a lot. Bye.